Hello.
Hi, Yusuke.
Yes, my name
Ah,
is Yusuke.
he-
Good
hello.
afternoon.
Nice to meet you.
Hello. Nice to meet you too. Yes. Okay.
So I'm Miguel. I'm part of the TNB chairs, and I'm gonna be
Nice to
chairing your
meet you.
session today. Nice to meet you. Um, yeah, so we're gonna wait a little bit for everyone to. Oh, you wanna record as well? Yeah.
If possible. Yeah,
Yeah,
I
yeah. We
try.
we
Yeah.
are we are recording it anyway. But
Okay. I got it. Yeah.
but if you wanna have it like it's uh
Yeah.
more
Thank you.
immediate, yeah, that's okay.
And can I check my presentation slide? And I'd like to share my
Yeah, I was gonna say
display. Yeah.
that. Exactly. Yeah, please. Thank you.
Thank you. And yeah. Yes. Also. I'd like to present this. Uh, can you view my presentation slide?
Yeah, I can also see your notes. I don't know if you want that as well.
Yeah,
Yeah, yeah.
unfortunately. No, no, no. I'm so
Yeah,
sorry.
that's okay.
Okay, and then, yeah, I, yes. Okay, then, yeah, uh, it's better now.
Yeah, now it's perfect. Yeah.
Oh,
Yeah,
great,
yeah,
great,
yeah, yeah.
great. Okay. Yes. Then I'd like to start the today's presentation, if possible.
Yeah, let's wait because Carl is not here yet.
I see, I
Yeah,
see.
yeah, yeah, yeah. Let's wait a bit so Carl joins and maybe some other people as well.
No problem, no
Maybe just
problem.
a couple of minutes.
Okay, okay, no problem.
So where are you based? Where are you living right
Yeah.
now?
I'm living in the Tokyo, Japan.
Okay,
So,
nice.
yeah, yeah. So I assumed, are you in the UK now?
I'm in the UK, yeah, in
Yeah, I see. So,
Brighton. I don't know if you're
mhm.
familiar. It's like
Sounds
South London.
nice.
Yeah.
Sounds nice. It's an 2:30 o'clock the PM in the UK.
Is what? Sorry.
I'm sorry, and it's the 2:30 PM. Sorry, and 2 o'clock. 2 o'clock
Yeah,
half.
yeah, yeah. Half.
Yeah,
Yeah,
yes.
half. Yeah, yeah, yeah. Yeah, I
Okay,
assume
and
it's
and
yeah, it's a bit late in Japan right now, I assume.
yes. Yes, yeah. In here, and it's 11 o'clock and
Okay.
half PM now. It's night
Not yeah, yeah, not
here.
bad. Do you manage to stay awake?
Yeah, yes.
Yeah.
But
Oh, okay. Yeah, Carl just joined now.
okay,
Yeah, yeah, everything. Yeah, we can see the slides nice, perfect.
okay,
So yeah, I guess then now that Carl is here, I guess we can start with your presentation, Yusuke. So feel free
okay.
to start.
Yes.
Thank you.
Okay, thank you. And good afternoon, everyone. It's 2 o'clock half PM in the UK, which means it's 11 half PM here in Tokyo. So good evening from Japan. And thank you so much for adjusting the schedule several times for me because I absent many few times these meetings. I'm so sorry. I really appreciate your kindness and understanding. I'm very happy to be here today, and I look forward to sharing my presentation with you. I'm Yusuke Hayashi from the AI Alignment Network, Japan. Today, I talk about the hidden empowerment in active inference. I will also show its extensions to body and symbols. Please feel free to stop me with questions. And today, I'd like to talk about, I'd like to start my presentation from the revisit the free energy principle. And we do not need to the bolt-on curiosity, rather, it emerges when we look carefully at the variational structure, especially the regularization term. And today I will show how minimizing that regularizer and stable constraints that is equivalent to maximizing a variational form of empowerment. That this provides a bridge from inference to control and sets up a path toward collective intelligence. And here is a classic loop, the environment to agent and back. The agent builds internal states to explain sensory inputs. This is the base for predictive coding and active inference. The agent updates internal representation Z to predict exteroceptive or simple the sensory inputs, or the action and perception form a closed loop. And we plan actions by lowering expected free energy. That this looks into the future, not only the present. It guides the agent to informative and preferred outcomes. And policies that minimize expected free energy are preferred and active inference. EFE combines the extrinsic value and epistemic value. And yes, and yes, this is a very famous equations. And EFE has two parts, the extrinsic value and epistemic value. The extrinsic value relates to the preference or goals, and epistemic value pushes us to reduce the uncertainty. This is a seed of curiosity, as you know. And with constraints, the intrinsic motivation appears naturally. That this points to the information gain, the control over the future perceptions. The curiosity is not a hack, it is in the objective. Yes, yes. And as you know, the many forms of intrinsic motivation match this view. That we can unify, I mean, the Koichi Takahashi and me can unify them under variational empowerment. It connects the learning signals with control signals. And let's consider expand the systems. And first, the extrinsic curiosity. Let's consider extrinsic curiosity. The seek informative outcomes from outside. We prove that world to reduce the ambiguity in our model. That this is a standard epistemic derive in the EFE. But we can also consider the intrinsic curiosity that to introduce agent's its own body. And the intrinsic curiosity tests our body and limits. and explore controllable state action manifolds. Ask what can reliably change or sense. And after that, we also go beyond to the corrective systems. Or we also we can consider the corrective curiosity that aligns the cause through the interaction. For instance, the social norms or joint attention or corrective curiosity is included, the hidden included in the free energy principle or active inference frameworks. And yeah, as you know, the language and symbols let us the share uncertainty and reduce it. That this leads to the joint attention or social norms. Yes, and when the agent begins to sense its own body, the space of prediction expands. Interoceptive signals or internal sensory inputs, for instance, the heartbeats or feeling hunger or fatigue, they become part of the generative model. This shift turns the self-maintenance into an intrinsic goal, not imposed from outside. The curiosity now includes the learning the body's own dynamics. Yes, yeah, the in this case, we consider the virtual agent, but it has its own battery. Then the feeling hungry or thirsty or tense are not just sensations, that they are prediction errors about internal states. So we need to introduce its own agent's own body to minimize them. The agent acts to restore balance or forming a homeostatic drive. These drives are intrinsic motivations rooted in the bodily inference. In this sense, the physiology itself is a, generator or of curiosity. Generator of curiosity. Yes. Yeah. So the body is important, and we can also to expand the active inference or free energy principle to the correctives. And beyond the body, the agents create the exchange, the external representations, the shared representations to the corrective. For instance, the words, diagrams, codes, and symbols that we can share with each others. But this symbol emergent system, we call it the symbol emergent system, introduces a new layer of interaction. The symbols act as externalized predictions, the allowing agents to coordinate shared understanding through this channel. Through this channel, curiosity extends into the social and linguistic realms. And when we then sorry, and when two agents attend to the same symbol or object, joint latent belief emerges. The language, norms, and shared attention function as corrective priors. They guide exploration not only of the world, but also of each other's mind. Choose the collective curiosity becomes a higher order intrinsic motivation. So we can understand agents, including ourselves, as entities standing at the boundaries of multiple extended environments or extended systems. The physical environment, the symbolic or linguistic system, and agent's own body. And we are standing at the boundaries of multiple environment systems. It is precisely from the dynamic interaction among these layers that various forms of intrinsic motivation emerge. The, each interactive system, the environment, body, and symbols, close its own loop with the agent. Together, they form a nested architecture of curiosity and control. The environmental uncertainty derives exploration, the bodily signals derives the regularization, and the symbolic exchange derives the cooperation or social norm. Yeah, and their integration explains the multi-layered intelligence observed, yes, in humans. So humans' intelligence is really complicated and fascinating. It has a fascinating aspect, the mysterious aspects. But let's consider these frameworks. Um, we can open its mysterious veils. I believe so. So yeah, today I'd like to. This is my recent working project, but I'd like to introduce at last this presentation. Uh, yes, and by coupling with multiple systems, the agent gains new pathways for intrinsic motivation. Every additional loop, the physical, the psychological, or symbolic, that expands its field to anatomy, sorry, the autonomy. This multi-system interaction is a richer of aspect of the self-organized behaviors. In essence, the new interaction systems invoke the new forms of intrinsic motivation. We can understand agents, including ourselves, yes, yes, answer pointed. Then next, we return to the basic math that I will show how exploration appears in the equations. That this prepares us for the understanding empowerment and the CPC. Let's start the conversation with on mathematics formula. The free energy is a upper bounds of surprise, as you know. It splits into the accuracy. I'm sorry. Okay, there's a point. Yes, and let's consider the surprise and fixed observations on fixed observations. And this surprise has an upper bound as a Kerr divergence. Then this Kerr divergence means of the surprise, and we can call it the variational free energy. The variational free energy decomposes into an accuracy term and complexity term or regularization. And this latter is often called the regularization. And the learning in this view lives in the regularizer by shaping beliefs to be simpler, more compatible with priors. We implicitly shape the future controllability. The key is to reveal how this regularization is tied to an empowerment signal. The yeah, I will explain the mechanisms after now, and so then we can introduce the expected free energy. It has a very similar or same structure of the with the variation of free energy. Let's see, at first the variation of free energy has an accuracy or surprise and regularization term, and uh, expected free energy that summarizes the policy variation as expected risk, the plus ambiguity or complexity. This offers a neat normative picture, but under the certain priors, they can dampen active sampling of informative states. And this expected free energy has the same structure, the accuracy or surprise and regularization term, and they are using the same approximation, and yeah, it's a change. The approximate the original prior P or generative model to the inference model or variational posterior Q. It approximate. Then we got the variational free energy or expected free energy. This is very important point. We use it after that, and 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 next we also approximate this KL term to read derives the epistemic value. We flip so we approximate this KL term, latter term, to the epistemic value. I'm sorry. Yeah. We can define the variational empowerment from that rewrite. It maximizes the mutual information between actions and outcomes. How this becomes a clear learning and control bridge. This is uh, yeah, as you know, the epistemic value is strongly related to the information gain. As you know, this latter term, the epistemic value is we can understand the negative information gain. That it strongly related to the intrinsic motivation or curiosity, but we can read another form of approximation formula. Let's see let's say that this green box, we can approximate it, the negative information gain term and the its residuals, or policy cost term. And ordinary approximation uses consider this term will be zero. It means the variational posterior Q equal the its prior P. But this is very a strong assumption. So let's consider these residuals. Then we can understand that these green boxes, we can approximate it as a negative variational mutual information. It combines the action and future observation or future latent codes. And then oh, sorry. Yes, then we can understand that this black boxes is strongly related to the minimizing this black box, green box term leads the maximizing variational mutual information. It leads the variational empowerment emerges. The empowerment favors states that we can both predict and influence. Such policies are naturally exploratory and informative. And as you know, that this term uh, means that it's the free energy principle has naturally intrinsic motivation or curiosity, and um, and so they support and stable running over time. And yes, so the variational empowerment, and yeah, the to act is maximizing one's control over the future percepts. The rewriting the expected free energy reveals the mutual information terms between the policy and the future outcomes. The policy KL minus empowerment motif as this formula that follows. The policies that keeps future observations, the controllable and informative emerge naturally. And by using this finding, we can understand the universal AI, it called AIXI, or we can understand it, the artificial general intelligence AGI. It's smartest the Bayesian reinforcement learning agent has a maximized exploration or empowerment agent. We can understand that. And let's consider at first the Shane Legg and Marcus Hutt proposed their idea, the AIXE. The AIXE is the most intelligent Bayesian reinforcement learning agent that designed to achieve the Pareto optimal rewards in uncertain environments. Its objective function has no regularization term, focusing solely on maximizing expected reward under a universal prior. On the other hand, the Google DeepMind proposed the self-AIXE. The self-AIXE, a learnable version that converges to AIXE, that introduces a regularization term within its objective. From its regularization, one can derive the information gain or variational mutual information. Then, and Professor Koichi Takahashi and me reinterpreted this idea as a variational empowerment. Therefore, AIXE can be understood as the theoretical limit of an agent that maximizes variational empowerment, revealing the central role of exploration in intelligence. This is our findings. The AIX's objective function and self-AIX's objective functions that will converge to the zero. The gap of the objective functions that will converge to zero. Then we can understand, and it's strongly related to the gap of the objectives is equivalent to the regularization term of policies, optimal policies, and between the optimal policies and learnable policies. And so this term means that this regularization term that we can rewrite to reinterpret as a negative the variational mutual information or negative variational empowerment. So the minimizing regularization means the maximizing the variational empowerment. the exploration. So the most smartest Bayesian agent needs to maximizing the exploration, the curiosity. This is our findings. And now we go beyond the single agent. That we ask how do symbols and groups change inference? This leads to the corrective predictive coding or CPC. This is a classic style of the active inference, the free energy principle, and and start with the standard predictive coding situation, the agent and the environment. The agent updates the internal states to reduce error. This is individual level. On the other hand, let's consider the adding external representations and symbol inputs. Now the communication changes each agent's inference. The shared codes guide the perception, each individual's the perception and the actions. Yes, the so CPC generates the predictive coding from the single brains to the groups. That each agent maintains a generative model, but brackets now exist between agents, mediating message passing of the prediction errors and codes. That this turns inference into the communication and communication into the joint inference. The, the, the diagram shows the agents linked by the shared external codes. That yes, that this is a shared or external representation. And the symbols that stabilize and spread hypotheses in the community by using this shared representation or shared codes, latent codes. This formalizes the scientific collaboration. And yes, this is our paper that we published this idea and in this March. And then, by introducing this framework, we can expand uh, the, the idea of expected free energy to collective expected free energy. And philosophically, the curiosity is not an external reward, but an internalized the regularizer. The system seeks beliefs that minimize the unnecessary complexity while maximizing the information that matters for control. This is why empowerment is naturally metric of autonomy. That it's quantifies how learning reshapes what the agent can bring about. That so the curiosity arises from the constraints on beliefs and policies that we modify the epistemic term under the blanket constraints. And this leads from the EFE to the collective EFE. We can derive the novel or epistemic value term. We call it the collective epistemic value. These terms, the classical EFE has the epistemic value, or for us that we can understand it the modified epistemic value or negative variational mutual information, and or we can also understand it the information gain, negative information gain. So this is not so new for us, but this term, this latter term is, I think, the new novel idea, the collective epistemic value. And yes, the negative collective epistemic value. So lowering collective EFE leads the maximizing or improve the collective curiosity or joint attention or yeah, yes. And so the CPC objective contains a collective regularization term, this term. And under the same decomposition, each diode contributes a policy divergence part of mutual information part. The minimizing the network regularizer, the choose shrinks the local inconsistencies and amplifies shared empowerment. So, i.e., for example, the groups the controllable information. This predicts the stable conventions of the efficient coordination, the cooperation. And the CEFE, the collective EFE, adds a shared regularizer on the external code, the WT. So each H is the policy care minus empowerment, then summed. The groups seeks joint attention were jointly predictable and controllable states. And then this is a conclusion, but today's my presentation. The first, we can reread the free energy toolkit. The free energy splits into the accuracy and complexity. The planning with EFE surfaces an epistemic drive. With constraints, this becomes empowerment. And information gain plus the control over observations. And second, we linked this to the smartest Bayesian RL agent, the self-AIXC as a regularizer, whose effect is variational mutual information. In the limit, the AIXC is empowerment maximization. Therefore, curiosity is a structure to the intelligence. It's very important to intelligence. And third, we scaled from the one brain to many. By adding the interception and the symbol channel WT, we obtained the CPC under collective EFE. Each edge optimized something like a policy care minus empowerment. The soul groups settle on states that are both predictable and jointly controllable. This is joint attention in action. Finally, the levers that we can tune are clear. The set priors that encode values and homeostasis. And second, choose regularization that rewards information seeking control. And third, the architect channels that let symbols emerge safely. With these, we can engineer empowered, the aligned societies. Yes, and yes, this is an today's my presentation's contents. And yes, I'm sorry, that's super fast, the presentation. I'm so sorry, but yes, the and yeah, and I can also explain about about I can talk on the CPC, but yes, yeah, today's my contents the variational mutual information, the variational empowerment, and it relates to the intelligence and collective curiosity or joint attention.
Cool.
Okay.
Thank you so
Okay.
much, Yusuke, for the
Yes.
presentation.
Yes.
So now if there are like any questions or comments, oh, I see Alex
Yes.
there. Hi. I'm just curious now, you show when you were showing the extra slides you had at the end, I saw information theory, rate distortion, and did I see something like that in your slides at the end? What's the, yeah, I would just wonder what's the content in there, what's the relation? What, yeah.
Yes. I'm sorry. Let's share my presentation slide. Okay. Yeah. So can I confirm your question? It means you'd like to understand what's the difference between the information gain and variational empowerment or variational mutual information? My understanding is correct? I'm so sorry.
No, sorry. It's you show there's some slides at the end of your presentation that
Mhm.
yeah, if you go, you were showing something about ray distortion theory and information theory at some point. I saw that in your
Ah,
slides. Yeah, in the appendix, exactly.
yes. Yes. Yes, and
Yeah, I was wondering
uh,
what's the content here.
yes, and
Yeah.
this is our working project, but my favorite project, and yeah, as you know, and Claude Shannon is a great mind. That he created the mathematical theory of communication, and the corrective predictive coding, the CPC, is strongly related to this theory. And let's consider the free energy landscape at the local minima. The communication channels, new communication channels emerge in the sense of the Claude Shannon, the mathematical theory of communication. We can derive that by using the mathematics. And yeah, I'm sorry. Yeah, this is, I'm sorry, an old presentation slide, so I cannot show the good picture. But yeah, and as you know, the variational autoencoder are strongly related to the Shannon's communication theory. As you know, that this is in classical the communication systems. Oh, sorry. I'm sorry. Oh. Laser pointer, laser pointer. I'm sorry. I'm sorry.
Well, yeah,
The
I can see that. Yeah, don't worry.
yeah. Yes, and in this case, the node of O means a message, and the node of Z means latent code, or yes, latent code, and we can decode it that, and we can recover the original messages, and this Bayesian network can transform this style, and this Bayesian network means the variational autoencoder. And yes, so the variational autoencoder is strongly related to the communication systems. And I'm sorry, okay. We can understand the predictive coding agents or free energy principle agents is strongly related to the VAE. I mean the let's consider the messages as a observation, and the latent code means a hidden environmental state. We can understand the communication channel framework as a prediction coding agent, and and we can extend the frameworks to the communication system, collective system, the groups, and by introducing the shared representation or external representation. Then uh, this Bayesian network means the each agent can communicate with each other by using this shared representation or symbols. But uh, some questions that emerges, the when and how these Bayesian networks emerges, when emerges that this shared representations nodes, and the answer is I'm sorry, the answer is I'm sorry, uh, Markov melding. I'm sorry, Markov melding. Markov melding is please, please wait. I'm so sorry. Bayesian networks can combine the connect with each other by using some fascinating techniques. I'm sorry. Please wait. Oh my God. Oh. Markov melding. Markov melding. Okay, yes, this one. Here. Uh, can you see this paper?
Yeah.
Or yeah, the joining and splitting models with Markov melding. That this paper tells us how to combine, the connect the two separated Bayesian networks. And I'm sorry. Oh, how can yes? Oh my God. Oh. Oh my God. Okay. Let's stop. Let's stop the pencil style. I'm sorry. It
No
doesn't
worries.
work. Yeah, but we can understand the when and how the two separated Bayesian networks at the local minima of free energy landscapes. Then uh, uh, communication channels the emerges, opens
Okay,
between
I
the
see, I see,
yeah,
I
yeah,
see.
yeah, 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 yeah. I'm so sorry. Yes,
Okay.
that's my our working project, but really
Okay.
interesting. But yes,
Perfect.
yes,
Yeah,
yes.
yeah, yeah, nice. Very interesting. Thank you. Yeah, I don't know, Alex. Yeah, I was gonna say.
Um,
Sorry.
yeah, thank you so much for this presentation. Been looking forward
Oh,
to it.
Alex Kiefer, I read your great paper. Thank you. Yeah.
Oh, thanks so much for mentioning that paper. Yeah, this is amazing work. I think you've gone farther than I have in a lot of respects. So there's a lot I'd like to ask about. I'm sure that I'm going to not get this quite right because I'm trying to communicate a lot, but just on the big picture first,
Mhm.
like, so I've been hesitating between the view that like exploration and curiosity and sort
Yes.
of reward seeking and risk minimization are orthogonal dimensions of sort of intrinsic motivation. And what I'm starting
Mhm.
to think more is that actually curiosity and exploration are more fundamental, and
Mhm.
that risk minimization kind of emerges as life comes under particular constraints uh, that life forms
Yes, yes,
take
yes,
on
yes.
this risk minimization behavior, but really the exploration is more fundamental. So it seemed to me that your big picture thesis was consistent with this. But so I just wanted to ask about so that this result you have, that basically it's, if I understood you, maybe just the first question is, did I understand you correctly that you said in the theoretical limit, an agent that maximizes variational empowerment, it sort of approaches this Bayes optimal risk minimizing agent, like reinforcement learning type agent. So
Yes.
yeah, I'm trying to understand that better. So that almost suggests that these are not orthogonal dimensions of motivation, but that somehow uh, the exploratory behavior converges to something that's optimal in the risk minimization sense. But actually, I don't quite get that, because so it seems like, sorry, I'm saying a lot here, but I'll stop in a second. But the it seems like you're saying that the empowerment term comes in through this approximation
Mhm.
to the AIXI objective. So
Yes, yes.
yeah.
Yes, as you know, the expected free energy are using the many approximation. Then uh, we can deep dive in the details or decomposition way. We can search the many decomposition way, and uh, by using some techniques, I think we can many variations of the compositions. Then and we need to understand the better upper bound or better lower bound of the approximation, and so the ordinary definition of expected free energy is this formula, and this formula has a strong assumption that so I state that and already, and the variational posterior Q and true prior P is equivalent. This is very strong assumption. And if then so if we consider the residuals or cost term, policy cost term, we can consider the novel term, the variational negative variational information, mutual information, and mm, so and the gap size of upper bound or lower bound is strongly related to the model's approximation skills. Then the parameter or model of variational posterior Q phi is really important to find the closer upper bound or closer lower bound. Then I think that the modeling the variational posterior is important. I'm sorry, and I couldn't consider the good answer to your question. I'm so sorry, and mm, yes, but yeah, as you know, there are many decompositions or approximations. And so, uh, yeah, I think we can derive the many variations of the expected free energy or free energy principle framework or active inference framework. And but the my understanding and your understanding is uh, sees the same direction, the free energy principle or active inference has a natural intrinsic motivation or curiosity or exploration. And this is intact the fact or aspects of the framework, the free energy principle, the active inference. So by introducing the new interaction systems, that we can introduce the novel curiosity or novel intrinsic motivations or homeostasis aspects or collective aspects, the joint attention. So yes, I think so. Is my answer is make sense? I'm sorry.
Yeah, thank you. I am yes. I mean, I have a couple other follow-ups I could ask, but whenever I anyone else wants to jump in, that's fine as well. Maybe I could ask one more question.
Yeah, go ahead.
To the chair we go. Okay. So thank you. No, that's I think I'll go through your papers in more detail again to refine my understanding. But I think I had a couple questions also about you introduced a lot of new elements here to me anyway. So
Yes.
the symbol connection to symbol systems, and then I found the idea of kind of curiosity about one's own model, or you could think of it that way. As that's very interesting. I haven't thought much about that. But just on the collective curiosity thing and the emergent symbol system. So and again, this might be something that I'd understand if I went. I need to spend more time with your written work on this. But um, how does this?
Yes, yes,
I
yes.
guess well, yeah. So I mean, I'm happy to just hear what you kind of say about it. My question was kind of so if I were intuitively, if I'm modeling an agent that's interacting with language, I would tend to just subsume that under, like, I would think that the way I interact with a symbol system is not, is fundamentally kind of the same as the way I'd interact with like memory traces, internal, right? There's stigmergic memories, things that I interact with. And the difference is mainly just the degree of epistemic access that other agents have to these structures. But like, if you imagine a very impactful event that everyone witnesses, you might imagine that there's similar internal representations that would be similar to the case of language. So I guess I'm just wondering where the dividing line is between, you know, how do symbol systems function differently in this framework from a more general engagement with the external?
Yes, it's very important questions. That yeah, as you know, yeah, and we distinguish the other sensory inputs and symbolic inputs because and words or languages or symbols is a, shared latent code for our frameworks. So we distinguish the normal sensory inputs or external internal sensory inputs or external sensory inputs that is just sensory inputs, but symbolic inputs is a distinguished representations for our frameworks because the we can communicate with each other by using the language or symbols. Then our brains has a same symbols in the each brains has the same symbols, so we can communicate with each others. So this so we can consider the symbol is a shared latent code or shared representation. As so, so the how can I say this is an example image, but and our brains connect with each other virtually, but and, by using the shared representations, that our brains connect with each other virtually, and so we can communicate with each other, and for instance, each agents are neuron, and groups or collective is a single brain. This is an analogy, but and thanks to the shared representation, and we can communicate with each other, and social Markov blanket or the Nobel unit or the emerges. So I mean the social or groups or collectives that emerges by connecting with each other by using the Nobel shared node. I'm sorry, yeah. So yeah, and we 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 can derive that it's the free energy or expected free energy, and its regularization term has naturally the negative variational mutual information or negative the information gain. So we can consider the individual levels curiosity or empowerment or intrinsic motivation, and also we can consider the collective level, group level curiosity or joint attention or intrinsic motivation, and and this aspect of frameworks is really important for us because the joint attention, philosophically, the joint attention or collective curiosity is strongly related to the emergence of symbols or languages or social norms or yeah. So, or let's consider the flocks or I'm sorry, the group dynamics that like a fish or the animals, the group dynamics that is strongly related to the joint attention or collective curiosity. So this term is really important to understand the collective dynamics. We think that. Yes, I'm sorry. Yes, I'm sorry, but yeah. So this is our working project, but we are preparing the Nobel paper that to explain our idea to you as sorry. Yeah. And is my answer is make sense? I'm sorry.
Yes.
Yes.
Thank you so much. Yeah, I want to, maybe I'll wait and see if anyone else has comments before. Yes. Thank you.
Thank you so much.
Yeah, I don't know if, well, Carl, if you want to jump in, or Alex extend on his comments, I'm happy with either. So
no, let Alex pursue his questioning. This is very interesting.
okay, perfect.
Okay, thanks, Carl. Yeah, I'll have to leave at 11. I have one more question. Well, yeah, lots more, but one more major one that is on my mind. So you also mentioned, I like that, I agree that there are implications for things like alignment, which obviously is an important theme for you with this work.
Yes.
So this, again, this is just something that's on my mind. I don't know what the right answer is, but so I guess I am this came up in a recent TMD meeting, actually. I'm I'm skeptical that we can accomplish that we can do a better job, I guess. So if you think, sorry, let me step back. If you think of evolution on the, this Darwinian sort of typical time scale, if you think of that as a process that's also driven by the same sort of objective, that's maximizing that's has a sort of curiosity, a drive toward empowerment, toward producing also just variety. Um, I'm skeptical that we can design better outcomes than that process. So maybe we could. So like if we're going to try to engineer specific outcomes, we're essentially placing further constraints on that, which could be fine. But I'm thinking of like, you know, this wonderful principle that sort of self-organizing systems, like the dissipative adaptation type stuff, that self-organizing systems become more constrained in order to more efficiently basically diffuse free energy. So I guess the question would be, how can we improve on natural evolution by imposing these constraints? And also, we might be in service of a larger sort of entropy maximization objective in doing that, but that won't necessarily get us the results we want. It will just help accomplish this process more efficiently at a larger scale. So anyway, big questions, but I'm curious what you think.
Yes, it's really big questions, difficult questions, but really fascinating questions. Yes, yeah. As you know, the evolution is really mm, difficult and problem and to understand. But and it's relate to the body or interceptive sensory inputs, and also it relates to the collectives or groups. And then it's not, it's not, uh, might not relate to the symbol emergent system, but it's have to relate to the collectives dynamics or group dynamics. So I think that to understand the evolution or what the macro scale, the dynamics, the phenomena, uh, we need to introduce the similar the frameworks, the body and the group systems, collective systems. As you know, the ordinary reinforcement learning frameworks just consider the physical environment and agent. But as you know, that we can feel the hungry or headaches. That it's related to the internal interoceptive the sensory inputs. So we need to introduce its own body systems. And also we, sometimes we feel the social norms. As you know, the ordinary Japanese feel every time the social norms, as you know, and then the social systems, the collectives, group systems is important aspects to understand the group dynamics or collective dynamics. And as you know, the evolution is related to the collective dynamics. Also, it's related to the its own body. I think the more missing link or more interaction systems, the novel interaction systems that we might need to introduce to understand the evolution. But yeah, I need that. Anyway, I believe that we need to extend the normal, ordinary reinforcement learning frameworks to more extended the frameworks. I mean, the novel interaction systems that we need to introduce. Is, is my answer? It makes sense? I'm sorry. Yeah, but this is my view. Yeah.
Of course. Thank you. Thank you. Thanks so much. This has really been really interesting. Thanks.
Thank you, Alex, for the questions. Yeah, Carl, I guess we can move to you now.
Thank you. Is it my turn now?
Yeah, I think so.
Okay, very good. Well, that was a wonderful presentation. Thank you very much. Everything you said was extremely compelling. And I'm mindful that Alex has to go in about 20 minutes. And I was going to, and you will see later that I was hoping that you could send Alex your work and your publications because they speak to exactly what Alex has been working on from a sort of conceptual and sometimes philosophical and sometimes more technical level. So what I might do is just address Alex's questions from my perspective, so that he doesn't miss the responses. But I just wanted to reiterate, this is fantastic work at many levels. I think, the joining the dots or relating different formalisms is exactly the right way to go, and I think is an enormous contribution. So for example, linking empowerment to curiosity, to expected free energy, to the free energy principle, linking that to rate distortion theory, linking both of those to collective inference and collective predictive coding and social neuroscience and collective belief updating, linking all of these to embodiment in terms of making sense of interoception and understanding how and what we can control. I think that is a very important contribution, and your derivations are you're also extremely, yes, and you've got an important one here. So what I'm going to do is just go through a number of points illustrated by papers, which I suspect you have already read, but if you haven't, they may be useful for you. Useful in the sense that they endorse or support many of the moves you've made right from the very beginning with this three-way or three different kinds of curiosity, right through to the emergence of shared representations that would be required for joint attention or communication, and the inherent importance of curiosity underneath that. So I repeat, some of the ideas and the work I am sure that you will already have know about, but I will show them for completeness. And because this is being recorded, you don't need to worry about remembering anything. I'm also aware that it's nearly your bedtime because it must be getting very late in Japan. So I'll try and go quickly and succinctly. But before I do that, just if I can, uh, Alex, in relation to you are worried that this formalism or this particular treatment of collective predictive coding surely can't do better than evolution, um, or a first principle account of any kind of self-organization. And I think you're absolutely right. But I think the response that I would have on behalf of our guest is that he has brought to us a particular decomposition of the first principle account of self-organization, even at an evolutionary scale, that has an interpretation in terms of collective or federated belief updating. So there's no engineering or designing here, because what he is doing is highlighting the curiosity or the epistemic aspect. It's not, I want agents to do that. It's more, I am curious about why that happened and what will give me the greatest information about it. Mathematically, I think you can see that if you looked at the equations where the epistemic value or the information again, the mutual information has been split into two with a collective and an individual one, you can see how you could motivate that separation. Excellent. I think we're about to see the equation. Um, if you imagine that there are certain kinds of outputs that can be split into two kinds, so O now becomes now becomes in fact there was another nice equation where it was where you derived the piece free energy, variational free energy under predictive coding, and then you had the next slide was the collective version where you split the you, I don't perhaps it was in the yes it must have been in the supplementary slides anyway.
Sorry. Yeah.
Oh, yeah, carry on. Go, perhaps that backwards. No, it doesn't matter. No, there was
I'm
one.
sorry. Yeah.
No, don't worry. We'll
Okay.
find it. It was the one where you had the expectations of ratios, where you'd split the.
Yeah.
Carry on. Go slowly, and then I will say stop when we find that
Yes, yes, yes. I'm
a
sorry.
good slide.
I'm sorry. Okay, okay, okay.
No, it must have been in the supplementary slides. It doesn't matter. And all I was going to say to Alex was, if you can
I'm
think
sorry.
about W and O
Yeah.
as both kinds of O's, or indeed W and Z as same kinds of Z's, um, then you're just separating out the mutual
I got
information.
it.
Um, or yes, that's the one. Excellent. Yeah.
I
So
got it.
yeah. So if we imagine now, let's pretend that the W's were not special and they were just say Z's. So the first term now becomes absorbed into the second term, and everything now becomes a standard expected free energy. So you have to ask yourself, well, what is special about the W's that can't be written as Z's? Well, there's an isomorphism between the latent states that are represented by these particular W's. And because these W's can now be broadcast and shared by many agents, they now become special outputs that have an isomorphism the uh, to the Z.
Yes.
So the
Yes.
shared representation with a common ground or a common language means that these W's play the special role of shared words that have an isomorphic or an identity mapping to certain Zs. So you can now just, if you like, split the usual information gain into two bits where one is special to the shared words or representations, the shared narrative,
Yes. 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 Yes.
and one which is not. So, and the one which is not, of course, is the observations that I have that you don't. So I can share now what I know because I'm seeing some O's that you're not seeing, but because we have a shared common ground and a shared reference, we can now
Wow.
update them. So the reason I'm making that point is that this is, if you like, a description of self-organization that you would find in evolutionary theory. And I say that because you can now say that Bayesian model selection is predicated on self-organization that minimizes variation free energy. And you can say that such systems also look as if they are minimizing expected free energy. And therefore, if natural selection is Bayesian model selection, this has to be true. And if this is true, then the collective regularization also has to be true if we share the same representations and the same language. So, Alex, what I'm saying is this is, if you like, a description of natural selection. It's just a,
Ah.
it is just a special kind of application, which is probably one of the most important ones, where we share stuff. We share the same generative model, we share the same Zs, and we can communicate that through the Ws that have an identity mapping to the Zs. So don't worry about that. Alex, you don't have to worry. It's all okay. It's just a beautiful interpretation of what it means for evolving, co-evolving with things that share the same generative model. I'll if I can, I will share my screen now and just
Yeah, please, if possible. Yeah, yeah, yeah.
and then if I can, okay, okay, that's
Super exciting idea.
now share my screen. Good. Yeah. Sorry. So this is for Alex. So this is just to remind me to say that, free energy minimizing to slow scale just is natural selection. And if it's natural selection, then you can now derive the expected free energy for any given phenotype in the population. So that was that one. Miguel's question about rate distortion theory. I noticed also the rate distortion was associated with the two, with the decomposition into expected information and extrinsic value, or the expected log evidence. There's this is not you, is it?
Me, yeah, that's me.
Oh, that's why you asked then. Right. So this.
Well, not necessarily, but yeah, I'm always interested in that intersection. That's why. Yeah.
So it, um, our guest, I think, would be, it would be useful. Sorry, our chair is actually very interested in rate
Wow.
distortion
Wow, wow, wow.
interpretations of variational free energy minimization. So this is again just to remind me that it would be very useful to send us your work, and specifically Miguel and Alex, the particular papers that speak to the sort of collective inference and the rate distortion um, um, stuff. And so let me just find. Oh, yeah. Oh no, that's not it. Where's and so here's you
Wow,
actually
wow. Yeah, 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 yeah.
you cited this paper. So
This is very good paper. Great
yeah,
mind.
yes.
Yeah.
So I just put it up to before I knew that Alex was here. I just put this up to suggest to remind me to remind you to send this work to Alex. But I
Yes,
don't need to
yes.
do that now
Thank you.
because Alex is actually here. So that's very good. So just this is what these are the papers that I thought you would find interesting or entertaining, just to substantiate this exploring or putting in place different domains in which curiosity was important. This is a non-technical paper that speaks to the importance of interoception, proprioception, and curiosity about one's own body. And it comes from a literature which focuses on in the life sciences, human neurodevelopment, and in particular something called the baby mobile paradigm. So there isn't any machine learning or active inference in this paper, but the ideas to explain the way that the baby mobile paradigm works are directly, um, I think, directly speak to your link with the body and interoception. So very briefly, what these authors are saying, in particular Elisa and Scott Kelso, um, is that we can explain the behavior of babies that are trying to learn about their own bodies in terms of a kind of curiosity. So the baby mobile paradigm is such that you have a mobile or a rattle that's tied to a baby's foot. And then what the baby does is it tries to make the mobile move by moving its foot. And originally, it was thought under a reinforcement learning paradigm that the baby just
Mm.
liked to see the mobile move around or make a sound.
Mhm.
But more recently, people have moved over to your kind of explanation, where the idea is, what kind of experiment could I do to test the hypothesis that I caused that? And of course, the best experiment, which has the greatest expected information gain or mutual information, is to wiggle and then stop.
mm,
and then wiggle, and then stop. That
mm.
has the greatest mutual information or the greatest expected information gain, and that's exactly what babies do.
I see. I
So
see. I see.
yeah, if you want to read this paper, you can, but
Ah, I see.
it is interesting
Yes, yes, yes.
the best explanation is
Sound.
exactly this sort of curiosity about what can I control? How can I use my body? So I thought that was nice. Um, the other example, which you may
Thank you.
know about, is the modeling communication. And this is a very simple example of communication through um,
Mm,
language and hermeneutics and linguistic communication. The reason I put it up
mm,
was that it all works. It all works um, on the basis of curiosity. So the whole
mm,
reason, the whole motivation for actually talking, asking questions. So in this particular example, it's a very small example, but it makes the
mm,
interesting point that the only reason for me asking you a question is that I am curious, that I can resolve uncertainty about what you
mm,
know or about what you see. So in this particular paradigm, one person could see two colored boxes and they were in a particular arrangement. The other person couldn't, but the other person could now ask the first person who could see what whether there was in this instance is there a square below. And the reason that they are doing that is that that has the greatest curiosity or expected information gain, given
mm,
given the agent's beliefs and what they're actually seeing. So I thought this was a nice example that is impacted in many directions using active inference and using exactly expected free energy that you presented to us that highlights the importance of curiosity for
mm,
communication, that the only reason to talk or to ask questions is to maximize, is to resolve our uncertainty or to
mm.
realize that intrinsic motivation. So I thought that was a nice example. The the closest thing that we've done to your collective predictive coding is federated inference.
I see. Yeah, I know this paper.
You do know
Yes.
that. Excellent. Yeah. So I don't need to go into any details. I think from your point of view, the most important thing that this work brings to the table is that the mapping between um, Z and W or
Mm,
Z and or the outcomes that now are shared
yes.
that mapping is the identity matrix
Mm,
or an isomorphic mapping. All this
mm,
paper says is that if you just simulate agents who are curious and they
mm,
all share the same world, then that identity mapping will emerge under free energy minimization. Again,
mm.
speaking to Alex's worry that
Wow, wow,
um,
wow. Mm,
that we're
yes.
going beyond evolution. This is just evolution. It relies exactly upon evolutionary arguments,
Mm, mm,
and in fact demonstrates that if a child has joint attention with its parents, then it will
mm,
learn that isomorphism between the Z and the W, and in so doing, increase its complexity. Um, yes, increase the structural complexity, which it would be.
mm.
I don't know, but it'd be very nice if you could somehow
Yes, beautiful cup.
um, translate this into rate distortion theory, or there was something you
Mm.
talked about in terms of the perhaps it was Alex and the tendency of things to become
Wow.
um, become better, more efficient free energy minimizing. From my perspective, as soon as you start to model other um, phenotypes or other agents collectively, um, then there seems to
Beautiful.
be a complexity arms race. So
Mm,
the emergence of greater complexity simply because you can now have to model and predict other things. And this is a very simple example. I repeat, from your point of view, what this doesn't this just supports what you have said, but just says that it licenses or enables you to say that W or omega, but let's call it W and Z do have an isomorphism simply
Mhm.
because that is an emergent property of any free energy minimizing process. And that then allows you to do the separation into the collective um, curiosity and
I
mutual
see.
information and the individual one. Um, um, so that was that, if that was useful. Um, Now, just coming back to Alex's point about you know uh, worrying about adding bits or to the expected free energy in a way that nature might not do it. Um, this have you are you aware of this physics work? Is this a paper?
Yeah, yeah, I studied physics at graduate school. Yeah, so I'm a big fan of the physics. So yeah, yeah, I know this paper path integrals, the particular kinds of yeah, strange and Bayesian mechanics, and I read your papers and uh,
Right. The reason I put this up is that your expressions for expected free energy, which you nicely then relate to um, XI, yeah, sort of universal computation and the like, but more specifically, the expected free energy
yes, yes, yes,
can be derived from first principles. So
yes, yes, yes,
you can't be wrong, as it were. In this paper, the expected free energy is written with an E as opposed to a G, because I use G for generalized, but it's got all the usual derivations. I think the importance of
mm,
this paper is that the expected free energy in exactly the functional form that you describe emerges as a natural consequence of self-organization. And the interesting thing is, of course, from the point of view of the physics of self-organization, the approximate posterior Q and the true posterior are the same thing by definition. So what you're bringing to the table is, well, yes, when I now apply it in terms of simulating under a given generative model, then I've got this gap, which is your R mutual information, which, if you like, is makes the mutual information into a variational mutual information. This doesn't address that, but what it does say is that the basic form has to be true. And then you can put the variational gap in. So I thought that was may be useful. Right, just a couple of um, just a couple of observations that in terms of the way that this is sold to the community. That I think it is important that when you refer to empowerment, you call it variational empowerment all everywhere, all the time. Um, I say that because Daniel Polanyi would have a more specific definition of empowerment, and I think you are using it correctly, just to stand in for a particular kind of mutual information that is controllable or is conditioned upon things that I can act upon. Daniel Polanyi would not quite define it so broadly or universally. And I use this paper as an example of a description of his particular definition, which does rest upon mutual information, but it's a little bit more complicated and involved than simply saying that to be empowered is to maximize the mutual information. He actually then uses that as a cost function for particular actions. So I'm just saying, technically, it would be a good idea not to use empowerment as a single word and then reference the empowerment community, but to always call it variational empowerment, and then you can define what you mean. And I think your definition is much more universal, much easier to understand, and of course, much easier to relate to the physics of self-organization through the free energy principle. But just a little note in case you find yourself on stage with Daniel Polanyi, and you're both using the same word to mean slightly different things. But this is a very good summary of what he means by it, and you will see that it's much more specific and much less general than just maximizing the mutual information in the spirit that you and I and your colleagues are using the word empowerment. Um, so I thought that might be interesting to say. The other person I think you should send your work to is Connor Hines. I don't know if you
Connor.
yeah, he wasn't at the active inference workshop, but he did his PhD with biologists who are experts on collective behavior and federated
Mm.
communication and inference. Like fish that swarm. But he also is very skilled in the free energy principle and the active inference sphere. Um, and I think he'd be extremely interested in your particular formulation of collective predictive coding. So this is one example of a number. This is not a particularly relevant example, other than it talks about belief updating together under the assumption that there are sort of shared meanings and shared representations. It does not simulate what you are simulating. I imagine that your work, you actually have lots of active inference agents who are actually communicating and belief updating. This is probably a bit simpler than that, or it might not. Well, it is simpler than that, but um, um, so it's not quite as sophisticated as your work. So the reason I am putting this up is so that I think you should send Connor your papers and say that I suggested that he'd be very interested in this particular work. Um, the other yeah, I put this up just with a smile, in the sense that uh, the stories that underwrite curiosity and information gain, I think, are
Give
really
me time.
interesting. Um, and you certainly highlighted one with respect to universal computation. I think that's an important story. Well, actually, let me just switch that. And I put this up as an example of one chapter in that story. The story I'm referring to here is the derivation of optimal communication and
Mm.
belief updating that comes from algorithmic complexity, cohomolograph complexity, that then led to minimum description lengths and minimum message length formulations in the spirit of rate distortion theorems, that then led to um, a brief consideration of minimum description length and cryptanalysis as a free energy minimizing process. So this is just an example
Mm.
from David McKay when he was a young man
Beautiful.
in 1995. And
Mm.
of course, this story then led to Solonomov induction, that then led to universal computation and to XAI. I can never pronounce it. The XAII universal computation of Hutter, um, and the like. So I found that intriguing, and I'd be very interested if you wrote a review of the history of these ideas and how they all converge on this notion of minimizing complexity or minimizing description length or maximizing compression or maximizing mutual information. To my mind, these are all the same thing and just different
Mhm.
ways of getting to the same ultimate objective function, which you've written down as an expected free energy here, and then gracefully decompose it into its
Yes,
various
yes, yes.
various parts. So this is one part of a story, and I'd be interested in hearing,
Thank you
you know,
for sharing.
if you come through that. And of course, that complexity um, minimization as compression is, of course, Jürgen Schmidhuder's big story. So he's been
Mm.
talking about this since 1991, and also
Mhm.
Jürgen likes to talking about this since 1991. In the context of, what would this look like? Well, it would look like
Oh,
artificial
artificial
curiosity.
curiosity.
Yeah.
Great.
So so he's been telling this a related story since the 1990s, but the story goes back much further than that, right back to Kolmogorov, I think.
Super
Uh,
fast.
and of course, once you've established that history, you can then look at the alternative, which of course would be Richard Feynman. So Richard Feynman did not deal with discrete Shannon-esque bits of information and large number approximations. He dealt with the pathological formulation, but they both end up via the variational treatment and variational free energy in the same place, which I think is, and then of course you're now taking that one step further and saying, well, now let's imagine lots of free energy minimizing systems all sharing something, which I think is, I repeat, a very important,
So great.
development. That is what I had to share, and I just wanted to thank you again. That was a very impressive
Yeah.
presentation.
Yeah, thank you so much. Thank you for sharing the great papers, the great researchers. Anyway, thank you so much. And I'm a big fan of the free energy principle and active inference. For me, the free energy principle is so beautiful for me. So, yeah, so if possible, in the future, I'd like to work with the TNB group, the researchers, the committees, if possible. Yeah. So anyway, thank you so much. Yeah, and can invite me. Yes, thank you so much.
Well, thank you, and I'm sure that the chairs and our particular chair here will be delighted to have you back when you've finished your next paper, so that we can discuss that.
Yes,
Yeah,
yes,
yeah,
I
absolutely.
have to.
Yeah.
I have to.
So, thank you so much again, Yusuke, for your presentation.
Thank
And
you so
thank you to you,
much.
Carl, as always. So, yeah, feel free to reach us again whenever you want to present something new. That would be awesome to have you again. So, thank you so much, both. See you, everyone, next time.
Thank you so much. I
Bye.
really enjoyed this meeting. Thank you so much.